Hello everyone. This may be one of my last videos, at least regarding this material. I might do some more after this, but this is kind of covering most of the electrodynamics that I want you to understand, at least at this level. Alright, so something important that I did not directly put in my notes, something called Kirchhoff's rules. He was a Russian man, and he did a lot for this field of study. And so these are the two rules, all right? It's the junction rule and the loop rule. I know my handwriting is not the best. I apologize. You know, kind of a funny and sad story. In elementary school, the only D I ever got was in handwriting. Most of you would not be surprised, obviously. But anywho, I have not gotten much better, so sorry, Mrs. Schaefer. I apologize. All right, the junction rule states that the sum of all currents entering a junction equals the sum of all currents leaving the junction. I know this terminology may seem off, but hopefully I have, Mr. Miyagi'd you, right? Wax on, wax off, into already understanding what these rules mean without having to describe them before, okay? So let me do two examples right here. Okay, say, I'm not gonna draw the full circuit, but just say I have one circuit that branches off into two different directions. Okay, so this is my circuit, and then my current, of course my current would flow in this direction. And then here's my junction. See right here where they kind of all meet and it branches? That would be the junction. Here, let me draw that different. This is my junction. So the current coming in is going to equal the current going out. Do you see that? I can call that just I, and then I1 and I2. So that means that I will equal I1 plus I2. Do you see that? And then also that works in the reverse order. Let me draw a different circuit. This time we'll have something like a fork almost. Okay. And then right here where they all meet again, this would be my junction. Okay, hopefully you see that. And so then all these currents coming in, we'll call this, oh whoops, red. We'll call this I1 coming through here. We'll call this I2 going straight down, and then I3 coming in this direction, and they will all converge right here. Okay, and we'll call this I4. So in this case, I1 plus I2 plus I3 equals I4, or I4 equals I1 plus I2 plus I3. Hopefully that makes sense. This works obviously primarily when there's parallel, when it's a parallel circuit, or when there are branches. If this were series, this wouldn't need to work, because if it's in series, there's only one direction to flow, and you wouldn't need this at all. So in series, irrelevant. The current is the same coming from the battery throughout the whole circuit. This only matters when there is some branching. Now, the loop law, and this is important for both series and parallel. I will draw some examples right now. So it says the sum of changes in a potential around any closed circuit must be zero. What in the world does that mean? Okay, so I will give you two examples. Okay, one very easy example. Another one might be a bit more challenging. So let's draw a very simple circuit. One resistor, two resistors, three resistors, and then going straight to the battery. So it doesn't matter. I'll call this R1, R2, and R3, and then we'll call just this the battery. Now what this means is that this is the most technical way of doing that. In our class, what I want you to understand is that the voltage coming of the battery will equal the sum of the voltages over here. That is not the best description in general, because there are many complicated circuits that could change this exactly. But let me write this in the way that it makes sense according to this definition, and also I will rewrite that into what I'm speaking of, which is the same thing for right now. So what this means is the voltage coming out of the battery. So we'll call this the battery or the total. I'll call it the bat right now, minus the voltage dropping everywhere. So remember, assuming, oh, I guess this is the positive side, so it should go in that direction. That's okay. But remember, when you have something with high potential and then you drop it, as it's falling, it loses all that potential. So you can say that the potential that it had at the beginning minus the potential that it used up would be 0, and that's what this is saying. So this would be the voltage from the battery minus the voltage from here, here, and here should equal 0. So this would be V1 minus V2 minus V3, or if you want, you could do a VBAT minus and then the sum of all these. That should equal 0. Do you see that? That's just conservation of energy. Something else important that I forgot to write is that this is the conservation of charge and this is the conservation of energy. Both conservation laws slightly different. This is like a physical manifestation. This is energy, right? Now let me rewrite this. Essentially what this is saying is that V battery equals V1 plus V2 plus V3. This is what I generally write it as, but this is the more technical route because when you get into more complex circuits, this makes more sense. But for right now, with the ones that I'm going to give you this year, this works just fine. Do you see that? Hopefully that works. Let me make a more complicated one. Let me make something like this, okay? Another similar one, we'll do it like this, because I will give you this problem later. Okay, yeah, that works just fine. All right, we'll call this 1, 2, 3, and then 4. Now, what this means is that here, look, there's only one loop. So this is straightforward. The sums of all of these voltages add up to the voltage of the battery. In this situation, since there is a little bit of parallel, that is not necessarily true. Okay, if I were to do just this as just a parallel circuit, forgetting these resistors right here, then the voltage of the battery would just see this one resistor here, again ignoring these ones, and then the voltage crossing this resistor would equal the voltage here, because depending on the loop that I make, whatever the resistors are in that little loop, that sum of that one loop has to equal the voltage coming out of the battery. But because these, you will not, an electron will not see resistor 2 and resistor 3 in one go around. You're either going to see 2 or 3. You're not going to see them both. And that's important. Because let's just say, again, you know, there's two routes. I can go this way or I can go that way. I cannot do them both in the exact same go around. So let me write this out, at least in this direction that we've become accustomed to. So let's just assume I go in this direction first. V battery equals V1 plus V2. But look, do I cross 3 at all? No, I go this loop and then I finish 4 plus V4, and that's it. Or I could go in this direction, and this would be V battery equals V1 plus V3 plus V4. Do you see that? So we know that V2 and V3 are identical. So that is the loop law. Or you could do V battery minus all of these equals 0, which is the technical way of writing this, but for this class this makes sense. So hopefully this is clear to you. Again, the thing that I do not want, and I want to stress this, I do not want you to write this VBAT. I'm writing in red so you know that this is bad. V1 plus V2 plus V3 plus V4. That does not work for this situation, because one electron is not going to experience this and this. It's just going to, you know, drop here and come down this way. It's like saying you drop something from a cliff, it falls, it goes up, and then it comes back down all by itself. No, it's not going to do that, okay? It's just going to fall straight down, and that is how this is written. So again, don't do this if something is in parallel. All right, let's get down to the problems that I've asked you to do. Okay. All right, I gave you a problem like this where I had the resistance of the 3 resistors and the voltage and the current coming out of the battery. I also give you a diagram. I will draw the diagram that I gave you, and then I will draw the one that I generally swap over to. So let me do that real quick. So this is the diagram I gave you. I gave you something like this. And then I gave you one right here. Okay, so these two are in series with one another, and this is in parallel with both of these. Again, I know that's an awful drawing. I apologize. Here, let me try a little bit harder on this one. Now, this will look almost, this will look hopefully very similar, with just a slight difference. At least when I was a student, you know, way back in the day. Again, this is a junction. Sorry, that's not a resistor. But this was easier for me to understand than this way. If that doesn't change anything for you, then all right. But at least when I was learning it, I remember that made it much easier for me. So positive coming this way. So we'll call this just R1 and R2 and then R3. Now, now that we've learned some of the rules, let's see what we can implement here, okay? So let's look at this kind of junction rule that I was talking about. Do you see how this is in parallel here? Well, coming out of the battery, this would be 12 volts. Coming out of the battery, there should be a current coming here that will split up this way and this way as well. Do you see that? This will kind of, and then it would converge later. So we already know the current coming out of the battery. It is 2. So I'm just going to call this I. We could call it I battery, but I'm just going to call it I. And then right here we can call it I1 and then I2 and I3. Okay, so let's see, before actually I write this down, let's look at this. Do you see R1 and R2? What do they have in common? I mean, forget about this, all right? Let's look at this. If I ignore this resistor, what can you say about these two? They're in series, right? So if they're in series, what does that mean about the current running through both of them? If you remember, that means that the current running through this resistor and this resistor is identical. Because even though, yes, this is in parallel with R3, it doesn't matter. The current flowing through here only has one way to go, so it's going to remain the same for both of them. So one rule I can say real quick is that I1 equals I2. I can say that. Now, remember the junction rule right here, this gets split off into here and here, and it will converge later and coming back this way. So I know that I, or I from the battery, is going to equal, and we can write I1 or I2, but I'm just going to write I1 plus I3. Do you see that rule? Okay. So I know now to check my answers that the current coming through here and, or actually before, this should be exactly the same. And then also one of these plus this current should equal 2. So keep that in mind. Now the other thing, let's look at the loop rule that we just learned. Okay, so let's go through both loops. So do you see how there's two different loops that I can do? I can go this way, or I can go this way out here. Okay, let's write that down. So the voltage from my battery, is going to equal, let's do this loop. Do you see how this is ignoring this? Because I can only, you know, an electron can only go through one of these routes at a time, is going to equal V1 plus V2, because this 12 volts has to be used up on the route that it goes. So it's going to be used up along here. Do you see that? Now, on the next loop that I could do, ignoring this one, okay, I could go here. And so that means that the V battery equals V3. Do you see that? So this means that the V from the battery equals V3, which equals V1 plus V2. So that means, you know what? This V battery just equals here. So let me write that down. That's going to be 12. Oh, look, I already figured something out. Okay. Now, there are multiple ways to do one thing that I've asked for, okay? So remember, this is kind of like figuring out like a little puzzle. I can either figure out R through the equivalent resistance, which I'll do both, or I could figure it out through just knowing that V equals IR. If V equals IR, R is going to equal to V divided by I, so 12 divided by 2 should be 6, right? But let me check my answer using my knowledge of equivalent resistance, because what if I didn't give you this and I just asked, hey, what is the equivalent resistance of the circuit? We should be able to figure that out. So let's do that real quick. Okay, so remember that these two are in series with one another and both of them are in parallel with here. So the R equivalent of the circuit, this is going to be a little complicated. Let's do this. Instead of doing the total equivalents all in one time, that might be confusing. Let's do it once. So let's call it R12. And what R12 is the equivalent of both of these. And since both of these are in series, I can just say that's going to be R1 plus R2. Do you see that? So I can combine these two into one first, and then I'll combine it with this later. Because I cannot combine this with these, think of it as like an order of operations. I can't, this can't go into that parentheses because it's not there yet. I have to do the parentheses first. So we'll call this R12, combine them, we'll call it R12. So R12 will be 1 and 2, and that'll be 10 ohms. Do you see that? Now that I combine these two into one resistor, I can combine this is perfectly in parallel with this. So my R equivalent for all of these, I guess there's no other resistor, will be, since they're in parallel, I have to do the 1 over R12 plus 1 over R3. Do you see that? So then R equivalent is going to equal to 1 over 10 plus 1 over 15 to the negative 1. If you do that, that'd be 30. That would be 2 over 30, 3 over 30, 5 over 30, and then to the negative 1, so that's 30 over 5. So my R equivalent for the whole circuit would be 6 ohms. Hey, look at that. Don't you see? It works. 6. And okay, and then that works this way or that works this way. So it's, I don't know, I always like when you can do things multiple ways and you'll come out to the exact same answer. That's when you know you're good, and you guys are good. All right, so let's figure something else out. Look, this should be another key to the puzzle. Okay, I have 2 knowns and 1 unknown. So if V equals IR, what does I have to equal here? So we'll call this I3 equals V3 divided by R3. So that's 12 volts divided by 15 ohms. Okay, that should be 0.8 amps. So that should be 0.8. Okay, so now I'm stuck. I don't know. This is one problem that some of you may have had. You may have been like, oh, I know in parallel the voltages have to be the same. I mean, some of you may have forgotten this part, and you might be like, oh, this is going to be 12 and this is going to be 12. And if this is 12 and this is 12 and that's 12, this will be 36. Bad mistakes. No. Okay? Remember that the voltage here and the voltage here has to add up to 12. And, there might be a way to figure this out, but something, let's look at what can I do to try to figure out one of these things. I know that both of these added together will equal 12, but I don't have a good idea as to, how to figure that out right now. Let's look at the current. Is there anything about this current that can help me solve, is there anything that could help me solve this unknown current? Well, let's look back here at this equation that we wrote. Do you remember the current here will be split off into these two directions? Well, that means that we already have I3. So if we have I3, I1, and I2 are identical. So remember that the current here, is going to equal I3 plus either I1 or I2 because they're the exact same one. Okay, so these have to be identical. So that means what plus 0.8 gives me 0.2. You should be able to do that in your head. That would be 1.2, 1.2. Do we see that? Because this is the same current, it doesn't change. So this plus this would give me that. Now we can find my voltage. Okay, now we can find the voltage. Okay, so if we did that, this times this, 7.2, this times this, 4.8. Hopefully that makes sense. Now for the moment of truth, it doesn't matter if it's in parallel or series or anything, all of the power of all of the resistors has to equal to the sum of the power coming from the battery. So all of these added together has to equal here. So let's do that. So remember Professor IV, or P equals I squared times R, or P equals V squared over R. Use, one of them to check your answers. I always do this first. So, okay, if you do this first, this times this will be, here, let me write it in black. This will be 24. Plug this into your calc, and if you do it this way, 2 squared times R, 4 times 6, 24, okay? You should do that yourself, but let me do these other ones. So R1, this times this, I already did in my calculator. That should be 8.64. This times this, that should be 5.76. And then this should be 9.6. And if you add them all up, it should equal 24. And if you, find this squared times that, this squared times that, this squared times this, or this squared divided by that, you should get all of the same answers. And that is how we know that life is good and that we are a talented group of individuals. Okay, on to the last but still quite difficult problem. This one I did not assign to you, but I think it would be useful to know how to do. Let me graph it real quick. Alright, so this is my next problem, my last problem for this video. Hopefully I gave myself enough room to do this. But again, my VIRP chart with the battery and then all of the resistors following. So this is the information I give you. Let's fill everything out, okay? So in black, let me write the knowns. So my total will be 12 volts. Let's do resistor 1 coming this way, and 2 and 3, doesn't matter, it could be 2 or 3, it won't change anything. So my value for my resistance here will be 9, 12, 6, and 5. Now again, some of you might just be like, oh, let me add all of these up to get my resistance. No, remember, these are in parallel, so I have to do that first, okay? I can add these two directly, but I have to combine these two before I combine it with everything else, okay? So let's just do that real quick. Since I didn't give myself much space down here, let's actually write it up here. So my total resistance, call it total, is going to equal to R1, and then I need to combine these, okay? So we'll just call it R23, because it's 2 and 3, and then plus R4. And I can do that because this is in series with all of this. So if I combine this into one, this will be in series with everything else, so I can just add them directly. But I need to find out what this equivalent is. So R23 is going to equal, well, remember, since these are in parallel, I can just do 1 over R2 plus 1 over R3, all to the -1. Okay, so let's do that real quick. That would be 1 over 12 plus 1 over 6 to the -1. If you do that, that'd be 112, 2, so 3, 3 total, 3 over 12, inverse that, 12 over 3, so that would be 4. Do you see that? So this will equal R1, which is going to be 9 plus 4 plus 5, that is going to be 18. If you want, you can slow that down, do it yourself, but this will be 18 ohms. Okay, and just like the Sudoku magic that we can do, look, 2 knowns, 1 unknown, let's figure that out. Okay, in this situation, you can write as a fraction or not, but know that V equals IR, so I is going to equal, my total I total is going to equal V total divided by R total, which is 12 divided by 18, so 2/3 or 0.67. Either way counts. I would prefer 0.6666 when you do the rest of these, but you know, if you round it, that would not be the worst thing in the world. So 0.67. Now, actually, maybe a bad thing, I jumped straight into calculations. I should have gone into equations before I even started. So just by looking at this, let's actually look at some loops and some junction rules to make sure we're doing all right. So look, do you see how this is in series with this? And this is in series with this? I know that the current coming out of this battery is actually going to equal the current going through this resistor and through this resistor as well. But that current will be split up unevenly among these two. So let's write that down in an equation form. So my I of the battery, or the total, is going to equal I1. Do you see that? Which is going to equal to I4. Hopefully you see that right there. Also, this current right here, which is the current that we're talking about, will be split up in this direction and in that direction. Do you see that? And then it will convert it back here, down here. So I1 will equal I2 plus I3. Remember, conservation of charge, okay? Those electrons, they're, you know, you're not going to go from 1 electron to 0 or 1 to 2. That electron's going to be that electron. It's just going to flow in one direction or the other. So that number in total stays the same. So we will do that later, but that's one, you know, an idea to keep in mind. Now the other one, remember the loop law. How many loops do we have? We have 4 resistors, but how many loops? How many directions can I, you know, go around this circuit? There should only be 2 different directions you can do. You can either go this way, or you can go this way. So remember, in our situation, we can just say the voltage drop throughout the circuit is going to equal the voltage of the battery, because this is the max that, you know, the max potential difference that's produced, and that has to be used up throughout the whole circuit. So let's write that in a different way. Okay, so my V of the battery is going to equal, let's do this route first, V1 plus V2, and then we don't use that one right now, we ignore it, and then we just do that, V4. Do you see that? Now let's go the other route. V of the battery is going to equal V1 plus V3 plus V4, and that's it. So we know that V2 is equal to V3. That's the main idea. Okay, so let's use some of these ideas to help us figure this out right here. Okay, so I found my equivalent resistance and then my current running through the total battery. But then I also remember the current coming out of here will be the same current here and here. So the total will be equal to I1 and I4. So that means I can just jot that down right now. Let me use a different color. So I1 would be 0.67 or 2/3, and then this would be 2/3. But remember, the current of 2 and 3 has to add up to this. And remember that the voltage here, here, and here adds up to 12, or here, here, and here adds up to 12. These are the rules that we have to live by. Now, can I use those rules to figure anything else out? Not right now at this moment, but what can we do, right? Let's go back here to this grid. 2 unknowns, or 2 knowns and 1 unknown. So we can solve this and this. All right, let us do that right now. 9 times 2/3, that is actually 6. So 6 volts passing through here. So already half of the voltage is used up right here. So that means the voltage of this and this has to equal 6 to, to add up to 12. But we'll do that later. Then we do 5 times 2/3. If you do that, that would actually be 3 1/3, or 3.33. Do you see that? That's going to be challenging, right? How do I figure that out? Well, actually remember, 12 is going to equal to this plus one of them, because they are identical, plus this. So these values will be the same. So I just need to find out what one of them is going to be. So to find out V2, right here, V2 is going to equal the V of the battery minus V1 and minus V4. So that's going to be, V2 is going to be 12 minus 6 minus 3.33 repeating. That's got to be 2.67, or 2 2/3 for both of them. And if you do V3, it'd be the exact same thing. Now that I have that, I have this unknown, and I can solve for that. Okay, but remember, it has to follow the rule of the current here and the current here adding up to any one of these currents. So let's do that real quick. I already have that rule, but I need to find this. So the way that I find it is by having 2 knowns and 1 unknown. So we have to do 2 2/3 divided by 12. If you actually do that, that's 2/9, and that's 0.22. And if you do this, 2 2/3 divided by 6, that's actually going to be 4/9, and that would be 0.44. Maybe I should write that out. I2 is going to be equal to V2 divided by R2. So that is 8/3 divided by 12. Yeah. So if you do that, that would be 2/9. If you did this, it would be the other way. Cool. It would be double that, actually, because since you're dividing by half of that, it would be double that. But anywho, so let's look. Does let's check this out. I2 plus I3 equals I4. Is that true? Let's see. I4 is 0.67, and then I2 is 0.22 plus 0.44. Oh yeah, this plus this will be equal to 0.666 repeating, which is this value. So yeah, that's actually true. So hey, we figured it out. Hopefully this was clear enough for you to do it. But again, let's do the power, because man, I just like making you do a lot of work. That's my goal in life. That's what I was put on this earth here to do, is just to make you work. Okay, remember, it doesn't matter really what the configuration of the whole circuit is. The sum of the power, no matter what, will equal to the power coming out of the battery. And that is equal to my Professor Ivy, or P equals I squared times R, or P equals V squared divided by R. Okay, I'm just going to do this. So 2/3 times this, that should equal 8. Okay, this times this would equal 4. This times this would actually equal 0.59. This times this would equal 1.19, and this times this would equal 2.22. If you add, I rounded it actually here, but if you add this and this and this and this up, it would equal 8. So hopefully that clarifies these kinds of problems for you. Good luck, everyone. Till next time.